All right, to start our lesson, we need to remember what the law of cosines is and how we set it up in order to find c. And also, we can also describe this length as the distance between 2 points, right? If I call this point x1, y1, and I call this point x2, y2, there's another way to describe the same distance. So let's do that first. Right, and we've known these equations since geometry, and both of these describe this same length c. We could take the square root, we don't need c squared, right? This length c using the law of cosines, but also using the distance formula. And usually the distance formula we just see as c with the square root. We're going to leave that out because it's going to be useful for these two quantities to be exactly the same, for it to be c squared and c squared. So this is 10.1, and you can look at the proof also in our book, but I thought we would do it together in class to get a little better understanding. Eventually what we're going to come up with are these four equations, but first we're going to look at, well, how do we just get one of these? The first one we're going to look at is cosine of one angle minus another. They're calling the angles alpha and beta. So, since you're asking yourself this question in blue here, let's take a look. So we want to find out what is the cosine of alpha minus beta, two angles. I'm going to recreate the diagram that the picture has. I'm going to draw two angles, one alpha and one beta. So really, just like in that beginning do now question we have a triangle, and I'm going to label this side C for now, just so that we can see, we can describe this length in two different ways. One using the law of cosines, and one using the distance formula from this point to this point. Also, before I write any more, if we want to label these points, well, if we're on our unit circle, then our radius is 1 here, and we can describe our coordinates with cosine and sine. Our x-coordinate would be cosine of this angle beta, and our y-coordinate would be sine of this angle beta. So I'm going to label the rest. And also, this angle in here, well, if this big blue angle is A, and this littler angle is alpha and beta, well then in between it's just the difference, right? Alpha minus beta, and that's where this piece is going to play in. So what I've done here is just plug in the information, very similar to what we did in the warm-up, but using this diagram. My side lengths, A and B, in my law of cosines are just 1, because I'm on my unit circle. So I plug that all in, and I finally see where this cosine of alpha minus beta, this angle here, is coming from. And eventually we're going to get it alone so that we could prove that it equals to this other side. I'm going to simplify now. Also in my distance formula here, well, I just did y2 minus y1, so I can do sine of beta minus sine of alpha, quantity squared, plus x2 minus, oops, that should say x1. I apologize for messing that part up. I'll fix that. That should say x1 there, so I'm going to do, again, cosine of beta minus cosine of alpha. Let me make that little switch. There we go, much better. So now I'm going to go about simplifying, and that's really the hard part of visualizing this and setting up these equations is done. The rest is just algebra. The right side's kind of ugly, and I noticed I have beta, sine of beta first, and then sine of alpha. Same thing with cosine beta, then cosine alpha. I'm going to switch those around when I simplify just so that we get the same order, alpha, beta, alpha, beta. I think it's a little easier to keep in your head. But I notice, oh, sine squared beta, and I have a cosine squared beta. We should know what Pythagorean identity that is, 1. And sine squared alpha and cosine squared alpha. So as soon as we FOIL this, multiply this, it gets ugly, but then it's going to get much more simplified using our trig identities. And my last step is to set these two things equal. Again, my goal is to get cosine of alpha minus beta alone. And that's where this identity comes from, or at least one of the ways we can show where this identity comes from. I just moved these first, alpha, cosine, and alpha and beta, and I put these ones here because generally that's the way we see it written, and that's what they asked us to show in the beginning. So that's the proof of my cosine alpha minus beta, my angle subtraction here, one minus the other. And we'll use this identity throughout our unit to simplify things or prove other identities. One last, it's not really a tricky proof or anything, but to find out where cosine of alpha plus beta comes from, we make a little substitution. The substitution I'm going to do is just that instead, in our equation we just proved, in this identity, let's change all of our betas, I got it right on the smartboard, to negative beta. So I'm going to make this little substitution, and I'm allowed to do this, right? We just proved this identity. That means it's true for any angle alpha and any angle beta. So in this case, I happen to say, okay, well, I want to make sure it's true, or I know it's true for a negative angle instead, because it's true for any angle. So I'm going to swap out this any beta I see with the negative beta. We're basically done now. We know that cosine of alpha minus a negative, this is going to become plus. That's what we wanted. For this part to simplify, we need to remember our negative identities. So cosine of negative beta, if you look back at your negative identities, is just cosine of beta. Sine of negative beta, well, the negative we can't just ignore it, but it's the same thing as negative 1 times the sine of beta. So this negative can come out front. And that's our proof for cosine of two angles added together, cosine of angle addition here of alpha and beta. So our rules, we've just proven both of these. Notice how this is written. If we started with the plus, like we just did, we have a subtraction in between. So we start with the plus, we have a subtraction, but if we start with the negative, like we did in the original proof, we got a plus. So those are flipped. Sine, we'll prove these another day, but notice these are the same. If you start with a plus of alpha plus beta, we get a plus here. We'll do that next time. Let's do a few examples just to use our rules today. It says find the exact value of cosine of 75. Well, if it said cosine of 45, we'd be done, right? We know it's root 2 over 2. But up until this point, we didn't know how to find any other angles. But now, because I have angle subtraction and angle addition, I can turn 75 into perhaps 30 plus 45. We know those angles. There are other combinations of angles that we know to get 75, but this is probably the easiest. So I'm going to go plug 30 and 45 in for cosine of alpha plus beta and expand it, and this way I'll be able to get my answers. So take a look. So this is certainly a slightly uglier number than something like root 3 over 2, but this is the cosine of 75 degrees. And by using my cosine of alpha plus beta identity, I was able to obtain that. Why don't you pause the video and see if you can come up with some way to find the sine of 15 degrees. Any of these combinations will get you the same answer. I'm going to use the easiest ones, 45 and 30, rather than like going into the second quadrant having to worry overly much about negatives. Now, if you do the workout like we did last time, you'll get the same answer, shockingly, root 6 minus root 2 over 4. But we kind of, I bet, you could have already known that answer. Look at this, sine of 15, and our last question was cosine of 75. Isn't this our cofunction identity? Cosine of 90 minus an angle is going to be the same as the sine of that angle, right? But anyways, that's our answer. The last questions I want to do for today is just going the opposite way. If I see some, confusing looking question like this, I don't know what the cosine of 50 is, I don't know what the cosine of 10 is, this might follow a pattern that we know. We might be able to simplify this and actually find the value. Cosine, 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 sine, sine, right? That's what we see here. Cosine, cosine, sine, sine. It has a minus, so if I simplify, I should have a plus. So this becomes right. In my second example, I saw this pattern, sine, cosine, cosine, sine. That's my sine of the alpha plus beta, or my sine of whatever angle plus another. We'll do these questions tomorrow. Don't worry about those. For homework, try these questions, and it's just practice with the same type of questions we did. I do want you to familiarize yourself with these identities. We're going to need to know these without too much thinking, so maybe make a little note card and come up with a way. We'll be deriving them again and practicing, so this wasn't our first run through and that's it. So we'll be practicing it again, which will help us stick it in our head, but do try to find some way to remember these identities, because they'll be useful not only this year, but also next year in calculus. All right. Thank you very much.